Okay, so welcome back. Where were we? So we were defining a fully connected neural networks, as you can see here. So we would like to check it again together. And as you can see here, we have these yellow boxes. So in the other slides from Morris, you have a very marked yellow boxes here. You see basically a background, yellow background, and these are the content that are relevant for your exam. So just take this in mind. So what we have here is an architecture where you have different layers, as we say. So we moved from a single perceptron to a neural networks. And what we are considering here is a fully connected neural network, which means that each of the neurons is fully connected to the next layer and with the previous one. So the question here is, how do we use this network for problems that are not for problems that are related to images, right? So the question is how to use spatial structure in the input and to inform the neural networks. And what we can say is that fully connected neural networks don't scale well to full images. Because as you can see here, if you have an input image like this one, what you should do is to transforming it into a vectors. And while you do that, you can see that what happens is that you lose the spatial information, right? Because at the end you make it as a vector. And this might not be the right solution, right? Because of course, what you are interested is to, if you have a good image with a good resolution, you might think that you actually want to preserve such an information in order to study, for instance, relationship between the neighbor pixels, right? So what we can say is that in the fully connected architecture, you don't consider the spatial information. You have a large number of parameters because at the end, as I said before, each connection is a weight, so it's a parameter that has to be learned. So you see, it looks like there are many disadvantages for using such an actor for image recognition problem, for instance. So we are looking for an architecture that basically makes an explicit assumption that the inputs are actually images, okay? So before we really didn't think about what, we just, consider an architecture and we really didn't think about of different type of inputs. But what if are images? So let's now consider this particular problem. So what you can say is that at the end, an image could be, represented as a two-dimensional array of pixels. And so here we see we are looking for something, for an actor that would be able to take into account this information, the spatial information, in order to deliver the same job. So to do the final decision, like class 1 or class 2, or so the different flowers, or anything that you are interested. Okay, so this is something that we want to do here. So, so let's now talk about how to do that, and let's consider the concept of locality. And we would like to incorporate this assumption into the nectar, into the architectures. So for locality, we means that generally objects tend to have local spatial support. So just imagine, for instance, the flower here. And if you get a pixel, and of course, with these images, you have a very high spatial resolution. So which means that over, for instance, a petal, of course, this grid is probably too big, sorry, but you may imagine that over this petal, you have actually many pixels. And if you just stuck on one pixel, you can imagine that the neighbor pixel will have the same, will be on the same object, right? Will be on the same features. And this is an important information that you should consider, for instance. This is not true. This is not just true for this kind of images, but of course also for instance, imagine an image which is acquired by satellite and is acquired over a particular area where you have, for instance, the house, a river, and you have pixel, for instance, over the roof of the house. And of course, pixel around central one of the house, they will still belonging to the same class. So you can see that this property will be present in many different types of images and should be explored. So how we can define an architecture, we can exploit this property. So the transition is goes from the fully connected unit. So as we saw in the previous architecture, each neuron is connected to everything, to all the neurons, which means to all the pixels. What we do here, we want to consider the locality, which means that now each neuron will be connected only to a particular region, which is smaller than the entire image. Right. So for terminology, this would be called a receptive field. So this window here, the local region that is studied by this particular neuron, is the receptive field. And you can see that by doing this, you can already imagine the advantage of that we reduce the number of connections, which means that we reduce the amount of computation, right? So here we consider locality, and the locality is for the reason I just gave it to you here. So we want to really exploit this spatial locality in images with high resolution. So we want to incorporate this assumption in the structure, and what we do is to basically, as I said here, so with images, it's not efficient to connect neurons to all the neurons in the previous layers, which means to all the previous, to all the pixels, but it's better to connect each neuron to a local region, as you can see here. So imagine here you have a RGB image, and what you do here is to connect only to a particular neuron in order to perform the operation. You can imagine now that also this, how big should be this spatial region is also a hyperparameter. So it's a parameter that you have to define in advance. So it's a filter size. And you can imagine that this could be chosen. So the size of this receptor field could be chosen according to the resolution that you have. So if you have, for instance, very detailed images, this could be, for instance, could drive you to have it a smaller one. And of course, if you have images with very low spatial resolution, like for instance, you have a pixel that is actually not so small, but is actually much bigger, then you should be careful not to take too big. Otherwise, you would just having inside a particular region too many different objects, right? So this is something that depends on your problems, and there are also a lot of guideline and experience that are already available in the community according to the type of images that you get. But again, just to stress out that as I promised you, deep learning can do feature extraction automatically, but there are still a lot of parameters or decisions that you should take into account. You should make them before in advance when you define such an actor. And this is basically the step where you spend more time now. So you don't spend a lot of time creating the feature, but you will spend a lot of time in designing the nectar. So deciding how many layers, what is the size of this filter, and other parameters, the activation function, and etc. So you see, the work is kind of moved on another problem. So let's review the convolution, which is basically the concept here that use exactly a small window on a particular region. So let's do it by just looking at an example. So let's say we want to classify an X from a set of binary images. So for the classification, let's say it would not be possible to simply compare the two images and check if they're equal, right? So if I do just a comparison and I see these are not equal, then I just say directly this is not an X. But this might not be true because the X might be not on the same shape, could be just be distorted, there will be some noise, so illumination problems, so anything that is related to the representation of the object might be different from let's say an ideal one, but it's still an X, right? So this is not the main strategy that you would use. So what you do the main strategy is to compare the images piece by piece. So it means that you want to search the important parts that define an X as an X. So you want to, again, looking for the features. So what are the features that are representing or that are basically ensure the existence of an X? And how you identify these features? Basically by learning filters, and these are the convolutional filters here that you find here. So think about each feature as a small patch, right? So you have a feature here, which could be like, this patch here. What you want to learn is a filter, right, that will be able to detect this particular feature. So you see here, what you need to do is to learn different type of filters, which will be able to detect the presence of a particular features. And once you detect the presence of a particular features, then you're done, because then you're sure that what you get there is an X. So you're sure that the presence of an X is guaranteed. Of course, here the problem is, how do we learn these weights? How do we learn these filters? So you see an example here. You see the X again, and you see an idle filter, let's say. So if you get this filter, if you're able to get this filter, and with the filter, we're gonna, go through all the image, and eventually we will end up to be on this particular region. And once you will do the multiplication and the summation of it, we will finally get an output which will tell me here is actually a perfect match, which means my filter detect this particular feature, which means that I can say that if all this feature will be then evaluated in the same way, finally I can say I got, and I can say that this is an X. So you see, we are working at local levels, okay? We are looking local levels, and this is basically the principle of convolution here. And this is what is the building block of the convolutional neural networks, which we are going to define soon. But in terms of terminology, what you see is the following. So you have your image, input image here. You will have your receptive field, your filter, and you will have particular weights, and they are the one that are put here small in red. And what you do is basically just start from the very top left, multiply the weights with the pixels, and then output a particular value. And the particular value, which is there computed by the convolution, will form the feature map. Okay, so here you have the image, the filter with the weights, and the result of this operation, which is the feature map. And this is exactly, this is very important, because the feature maps will tell you basically where the input was activated by the particular filter. Okay, so if we get feature maps with a particular value, we will be sure that the features were detected, and we can then finally do the final decision. So generally speaking, there are many different filters. So we know a lot of type of filters a priori in image in the domain of digital processing, image processing. So you have, for instance, see different type of filters here that you can already use in advance to detect some particular characteristic of the image. But this is something that we know in advance for these problems, but we don't know them for more complex problems, for any kind of problem that we might encounter during our research, right? So this is something that we need to learn, right? So these weights are the connection, the local connection, and now we have in the new architecture that has to be learned. So how would it look now, a convolutional layer? So I try to make it as clear as possible by rotating this example. Let's see if we can manage. So what we have usually in a single layer now are basically n filters with different set of weights. So imagine now that you want to define two filters here, and each of the filter will have a particular spatial region. So you see here you have your receptive field of 4 × 4. In the domain space, you have the 3 channels, because in inputs, for instance, here you get an input an RGB image. And what you do is exactly the convolutional operation across all the spatial position of your image. And what you get is the output, right? Which is gonna form your feature map, right? So here what we have 2 filters. So we will start with the first filter, we will go across the image, and for each of the spatial location we will get an output, which will form the final feature map, which is just another image. All right. And you might want to, and you're gonna use different type of filters. So you're gonna have to use different filters, right? Because each filter will be able to detect some particular features. If you remember from the example from before, from the X, one filter is not enough. You need to have, like here, you might need to have different filters that has to be learned in order to be sure that you will identify the 3 particular features that define, in this case, the X, right? So what happens is that at the end, once you do this, you will get to an output, which is a cube, which will be include different feature maps, and usually you have many of those. So when we talk about, a convolutional layer, you should imagine something like this. So you have, your operation of convolutional operation that goes through over the image, and it will produce a feature map. And you will continue later on. So imagine that then you will have to stack this. You will start then, once you have the feature maps here, you will do the same over the feature maps with new filters, and you will obtain new feature maps, and you continue. So you will have many different layers, right? So this is one layer, but you will have many of these in subsequent layers, in order to to go deep and find different level of abstraction of different features. So this is the idea. And another important aspect to consider here is that if you remember, we started by moving from fully connected units, so where we have each neuron connected to everything, to a locality property where we said, okay, now we are just connected to a small region, in this case, the convolution. But another important aspect is that when we do this, we actually consider the same weights. So the weights that I'm using here at the very beginning are the same weight that I will use later on the next step, and etc., right? So it means that we are sharing the weights. And this is done by an assumption of the translation invariance, which means that if you have an object on an image, for instance, doesn't matter what it is, right? It doesn't matter if it's on the left side, if it's in the center, or if it's on the right side. It will just, it will have the same appearance, which is independent by the location, and you want to exploit this. And of course, here you can imagine that we are now even proceeding further in terms of, let's say, less computation, because we are now going to have different weights for all the different possible locations. So it was already nice to not have all the connection here. But of course, if we do this, if we have different connection for each of the location, you still have a lot of connection, right? So you still end up in a lot of computation. So by doing this weight sharing, this gets much better, right? Because at the end you share the same weights for all the inputs, which means less computation. Okay, so hopefully I didn't confuse you too much, but this is what you can imagine when we talk about a convolutional neural network. So here you see again what we started from this kind of network where everything is connected from the input layer to the hidden layers into the output layer. What we decided is that if we have an input image like this, it's not probably the best idea to stretch it as a vector and lose the connection and lose the spatial information, but it would be better actually to have an architecture which is able to study the spatial domain step by step. So by scanning the image all over and produce a feature map, which is which is according to the type of filters that you're learning. So you see the weights. So the weights are much less because, you know, if you were on this architecture, we would have to connect all the pixels in the image to the next layer, but this is something that we don't do here. We just share the weights and we do the locality. And what we've seen until now is that after you do this operation, you obtain different feature maps. So then what you might usually see in an actor like that are the pooling layer. I'm not entering into the details here, but just imagine that you do the same. So by studying, for instance, small patches, and what you do is basically to extract one particular value. So you reduce the dimension of it. And this is done also for the computation, but also for you know, redundancy for the features. So just, you know, it's very easy. You just scan the image, and according to a particular operation, for instance, you might take the average of the maximum value, you just extract one value, and then you create a new feature map here. And you continue, right, that you have different layers. And an important thing is that at the end, if you still want to do classification, you wind up again on a fully connected layers, where, you know, each of the neurons at the end will represent the probability of a particular class, right? So this is basically what you expect in a convolutional neural network. There's a lot of material online, many different you know, tutorials. Some of them might be confusing with the terminology, but, you know, just try to, if you are more interested, to have a look at them, and you will see that this is basically what it's all about. So if we now look, for instance, in a possible application here, for instance, you know, detecting different type of I don't know, cars or airplanes, so different type of transportation methods, I would say. So you see that what you can obtain is that in different convolutional layer, so you see you start from the convolutions, like, so you will start from the input image, you will just go through over the image and you will get this, feature maps, right? So how many feature maps you get according to how many filters you're using. You will activate them with an activation function, as we saw before, for instance, ReLU. And you will continue, you can apply also pooling to reduce the dimension. But what is important here is that you see, this is actually the promise that of deep learning is that you will start from a raw image and you're not gonna provide any attributes, any features by a priori. You will just let the nectar learn it with this filter, with these filters. And at the end, the nectar will have to basically find out what are the best weights, so what are the best filters that are able to solve a particular problem. Because remember, at the end, the goal is the same. Once we learn the features with our training set, so with our, for instance, you know, training set of images of cars, truck, airplane, we still have the labels, remember. At the end, what we want to do is to have an actor that, you know, when I come in the future with a new image, we will be able to tell me this is a class with a high fidelity confidence. So again, this is again another, let's say, view of it. I mean, probably now you are you're understanding it. So we have the input, and we have these different types of, you know, repetitive layers. And this is exactly the feature learning part. And so where the magic happens, so where the features are learned automatically with the convolution, the activation function, and pooling. And at the end, you end up to have a series of fully connected layers, which will enable you to then arrive to a point where you can do the classification. And this would be very simple because everything, you know, complex is done here. So the learning part is, the more complex part is done when to figure it out which are the filters. And so this part makes the final classification problem easier. So now the question is, okay, I told you how a structure of a convolutional neural network is done. You know, what are the weights, how they're connected, how do we deal with images. Now the question is, how do we learn the weights? Because at the end, if I just give you an architecture like that with random weights, so we random weights on the different connections, random filters, these are just not optimized for the problem. So if you remember, we have to do we need to do the trainings, and the training basically is that process which will find out which are the best parameters, the best weights for your particular problem, which is represented by the training set. So we're looking for an algorithm to do that. And we were going to talk here of one of the main, basically the one that has been now established in the field, which is backpropagation, which is a gradient-based search method, which allows you to find the minimum of, for instance, as here a loss function, which is represented by the sum of the square error criteria. So here we consider a simple loss function, simple example, just for clarification, but there are more complex loss function that you might consider. But here the thing is just to give you the ideas that you start from a training set, so a set of images, right? So we will have a number of training samples, so a number of images, for instance, of the flowers. Each of the image will have a label. So each of the image will have a label which tells this is class A and class B, right? This is something that has to be done a priori. And once you have that, you will start to, to input each of the image to the training, to the nectar, right? And so we will just go, let the image go through the nectar, and the nectar will give us an answer, right? It will give us an output at the end. And what we can do is basically compare the output with the expected value, because we know that the image that we give is class 1. And what we can do, we just compare it and then, do this for all the training samples. And then the final goal here would be to minimize this error, because at the end we want to be sure that every time we put this image, which is part of the training set, will give us the exact answer, which we know, and we can exploit it in this way, okay? So this is something that we check at the end once we put all the images inside the network. And this is basically how the backpropagation algorithm works. So it's based on 3 phases. So first of all, you have all your images, which belong to the training set, which will be, pass and let them through the neural network. Here you see the multi-layer perceptron, but could be a convolutional neural network. So this is a algorithm which is agnostic to the type of architecture you have, right? So once then you will have an answer, you will have to compare the answer to the actual truth, so the labels that you already have from your training set, and you will then propagate this back, and we'll see how does it work in order to do an update of the weights. So at the beginning here, we will have some particular weights. So each connection will have a particular weight, which is random at the beginning. Of course, there are also strategies to initialize them with not a random procedure, but let's now assume that these are randoms. And after the first propagation phase, these weights will be slightly better for this particular problem. And this is a phase that will continue all over until we are not sure that the weights will be optimal, at least for this particular training set. So the question is how to use this, the loss, so this function, to iteratively update the weights over a given, the training data, right? So we have the loss function. So this is the loss function, which basically compare the output with the desired output. We have the weights, right? Because at the end, the output of the nectar is just based on the type of weights. So this is basically the nectar, the function. You have the input and the weights, and each of the training sample, according to the weights you have, it will give you an answer, right? And this answer will be compared to the desired label, and the loss function will give you a value, right? So this is what we want to minimize. And the only thing we can change, you can see, are the weights. These are the only thing that we can optimize. There is nothing else we can change. The labels are there, the inputs are there, The only thing we have to change are the weights. And with this, you know, a bold notation, we mean all the possible weights inside the nectar. So the weights from the layer 0, layer 1, etc. So these are all the weights, which could be small if you just consider a small nectar, or very, very, very big, a very big number if you consider a deep neural nectar. So let's visualize it. Maybe it will be a bit, I don't know, simpler. Let's just consider, for instance, a nectar with just two weights. So you see here we have weight 0 and weight 1. So this is very small. It's not even a nectar, but just to visualize how a loss function could look like, right? So as again I said, we have two weights, and these are the only parameters we can change. And according to the weights, the loss function will give us an answer. So here is the answer that the loss function gives to you, and the goal is to minimizing it. So what usually we do, as I said before, we have a nectar, we have an architecture, right, with random weights. So we will start somewhere here. So we will have a particular random value for weight 0 and for weight 1. It might be located already, you know, in some minimum, but in this case, you see, is in a bad position. So what we can do is to compute the gradients at these local points. So according to the respect to the weights, and in this landscape, the gradient will tell us the direction of the maximum where it basically starts to grow. And this is just from math. And what we are going to take is the opposite direction. So we kind of say, okay, for this particular weight, the loss is too high. So let's compute the gradients and find out which is the path that will hopefully lead me to the minimum. Right, to the minimum means the minimum where the weights are optimized for solving a particular training data set, so a problem. So basically, we will continue this with this iterative procedure all over and over, and all of this step is basically, you know, passing all the data, passing some part of the data to the nectar, update the weights, and then find the direction. Continue until hopefully you will get to the minimum. You know, I don't have much time for this, so I post here a video. I think this is a very nice explanation of how this works. I just, you know, summarize here the results, but if you have a look of this video, you will learn how it works with the very simple nectar. So you basically have just one input, one weight, and an output, and this will guide you and show how, by starting from a random weight, you will be able to find the right weights step by step. So you will be able to find the optimal weights that can solve a particular this particular problem. So this is something that I encourage you to watch. So hopefully we'll clarify a bit all the concept that I just summarized here. So here is the backpropagation algorithm. So just a summary of it. So this is a concept that you might remember for the exam. So you basically have an nectars which are completely random weights, and what you want to do is to find the best weights for the particular problem. So you will have to have this loop, and you will continue until you reach any convergency. And what you will have to do is to compute the gradients, right, of all your weights. And you can imagine now that this is the very computational part, right? Because this can be very computational if the nectar is very deep. So you have a lot of weights. And this is exactly where, for instance, GPUs are playing a very important role for this particular step. And we will see that in the next lecture of Rocco Sedona, how this can be actually parallelized. So actually you can parallelize this operation and perform it over different devices, different GPUs, in order to make this faster. And as I showed you before, what we do once we compute the gradients, we update the weights by taking the opposite direction to the gradient. So we go down. And we will do it. So this is the concept of learning rate. I was also mentioning before. Also, there is on the website. If you remember, there was this parameter, and this basically just decide how big is going to be your step when you move from one point to another on the loss function. So it basically determines how much do you trust? And this can be fixed, can be learned even, can be adjustable. There are many different, let's say, strategies to do that. But here, just a message that I want to give you. You can see that according to how you choose, you might end up in a situation where maybe it is too small, so it takes a lot of time to get to the minimum. You might get it too large, which means that you will just jump around the loss function without actually converging at the end. Or you might actually find a good one. But of course, this is something that you need still to learn, to find out based on experience or the problems or guidelines. Because this is very crucial. You can see that if you just have a mistake on choosing this parameter, everything will be compromised. So you see many parameters, many things to choose in advance when you define your deep neural network. So you can imagine now here we're just considering a loss function from here, just two weights. So remember, just if we consider a small neural network with one hidden layer and a different connection, it means that these weights are, this dimension is increasing a lot. So we're not just talking about one weight or two weights as before. So it means that finding a minimum will be very complicated. So this is something that this is the main deal here, to find hopefully the minimum. And as you can see here, just if you consider one example, one weight, you might end up and stuck in local minimums or some, or it really depends of your data. So the loss function will basically be determined by the training set that you get in the input. So and here just to summarize this, at the end, when you consider a problem, so you learn from a particular set of training sample, right? So what basically you are saying is that all the images that you get from the flowers, you're basically assuming that all these images are representing all the possible variation of the flower that you might find in nature. So it means that you have all the possible combination, all the possible status. So you are basically say, I hope that all this training set will be able to represent all possible flowers that I will find in nature. And you can imagine this is quite difficult to ensure. It's probably not true, but hopefully if your training set is good enough, you will be able to find a minimum that you also will generalize on new data. Right, so again, what we are minimizing is on a particular training set. We are not working on the true loss, okay? We will never be able to get all the possible training samples representing all the possible status of the flowers, for instance, on different, for seasons or, with diseases, different, acquisition from different angle with different lights. So you see, this is something that it might bring to think about, okay, but then it's impossible because, if we will never have a training set that is able to represent the whole world, how can we pretend that our nectar will be able to find a good generalization? Well, this is done. This can be achieved by different techniques, for instance, which are, for instance, improvements of the stochastic gradient descent, where basically you use different methods there. You use, for instance, some other optimization where you want to maybe to skip some connections. So these are very advanced methods. These I cannot really go into details. For instance, you use different adaptive update rules for the weights, which are not, from the stochastic gradient descent. You use the adaptive learning rate, for instance, so you go maybe slow at the beginning and then you continue faster, or the other way around. You use different type of batch normalization. So you use a lot of data, but of course data, they don't come for free, right? So, and at the end, you will not still have all the possible data available. You might want to augment the data. So just to tell you that, there are different, different strategies, a lot of research around here to make sure that what you're learning, even if you have, not a big or large amount of training set, you will end up to learn something that also might work for for different and future problems or for future samples. So here just an example, a different optimizer instead of SGD, how it might work better. Just choosing a new optimizer. If you have also very simple loss function here, but you can see here that, for instance, stochastic gradient gets stuck here, and other type of optimizer will be able to reach the minimum much faster. So a lot of research here, a lot of methods that also can be used. Okay, I think I'm running out of time probably, Maurice.
Yeah, it would be good to come to a close
yes.
soon. Yeah, thank you.
I will just stop these 2 slides. Just last message. So deep learning is transforming actually how we build supercomputers. You can imagine why. So not just because now we have a lot of data, but also because the nectar are getting more complex. Here you see, for instance, just a trend since, well, actually a long trend from the perceptron. And actually you can see here that all over the years, the computation demand is much higher. And just please remember that this is not just about the number, the size of the data or the complexity of the nectar, but also new techniques how we use to learn. So different methodology that we use to apply as a learning strategy for these nectars. So we are building new supercomputers also at JC, at Jülich, basically tuned for these particular problems. And here just like an example of one of the last models that's been released. These are for natural language processing. And you can just see here from the previous version how the number of parameters, so the number of weights, remember these are just the weights that you need to learn and optimize, has been grown. And of course, this is something that requires high computation in order to, to do this in a minimum amount of time. Right, so I will just stop here. These are the last slide that just related to big data. You already saw this in the lecture. How we can define big data, what are the definitions, and the last 3 slides basically are just how we define big data from my domain, from remote sensing, from satellite data. This is something for you for information, how we define the concept of the velocity, volume, and variety. But this is something for you just to see, that big data is not just about volume, but there are big data defines many different aspects that you want to consider. So I will stop here. Hopefully I was clear enough, and I'm really looking forward to answer any questions that might appear now. Thanks a lot.
Yeah, thank you very much. Yeah, if you just continue with the references for those that just see the video, I think it's good to go until the end of the slide set, because some maybe don't get the slides really directly when they go to YouTube or so. But I think once again, very much thank you. I think it was an excellent lecture, very clear, very nicely put together. And of course, we hear something about this gentleman there, Rocco Sedona on the right top there, a PhD student of mine on Thursday. He will also pick up, of course, many things from the remote sensing we just heard, but also from the general idea of putting deep learning in clouds and parallel computing and distributed computing environments.